Hello viewers, welcome to online course on Mathematics 3 for engineering field. Today we are going to discuss about the Laurent series, some related example. Myself Sanjay Vishwas, Assistant Professor of Mathematics, Department of Applied Science and Humanities of Guru Nanak Institute of Technology. Here is my details of contact information. If you have facing any problem regarding my class, you can call me freely or send message with my mail id sanjay.vishwas@gnit.ac.in. Let us move on the next slide. Today we are going to discuss about the Laurent series on the chapter complex integration. So here is the content of today's lecture. At first, we are going to discuss about the statement of Laurent series, about any points and some notes on Laurent series. After that, we will take some examples on Laurent series. First, we will begin with the statement of Laurent series. Here is the statement. So, if a function f of z is analytic in the annular region, capital D. Annular region means, okay, this is actually the annular region. There are two circles, C1 and C2. So in this portion is called the annular region. Okay, so D is the annular region bounded by two concentric circle, C1 and C2. What do we mean by concentric circle? So concentric circle means where the center at the same point for any two circles. Okay, so here C1 and C2 be two circles, and alpha is the center of the circle C1 as well as circle C2, and C2 is lies wholly within the circle C1, and R1 and R2 be two radius of the circle C1 and C2, where C1 the radius R1 is greater than radius R2. Then for all z belongs to D, and D is the annular region bounded by C1 and C, then f of z is equals to summation n is equal to 0 to infinity an into z minus alpha whole to the power n plus summation over n is equal to 1 to infinity bn into z minus alpha whole to the power minus n. And we can write down this equation number 1. Okay, where an is equal to 1 by 2 pi I close integration over C1 f of z by z minus alpha whole to the power n plus 1 dz, where n is equal to 0, 1, 2 and up to infinity, and bn is equal to 1 by 2 pi I close integration over C2. So here is the circle. Okay, this is actually C2, and in the first case there is a circle, and this circle is C1. And C1 is the bigger than C2, and C2 is lies wholly within C1, and therefore the Bn is equal to 1 by 2 pi I close integration over C2 f of z by z minus alpha whole to the power minus n plus 1 dz, where n is equal to 1, 2, 3 and up to infinity. Then the equation, that is our series 1, is called the Laurent series of f of z about the point z is equal to alpha. Okay, now we replace n by minus n, then from an we'll get a of minus n, and this is equals to 1 by 2 pi I close integration over C 1 f of z by z minus alpha whole to the power minus n plus 1 into dz, and you know this is equals to bn, the value of bn. So hence Laurent series can be written as f of z is equal to summation over n is equal to 0 to infinity an into z minus alpha whole to the power n plus summation over n is equal to 1 to infinity a of minus n. Okay, in this case you know b of n is equal to a of minus n. If we put n by minus n, or replacing n by minus n, we'll get a of minus n. Okay, and a of minus n is equals to or same as the value of Bn. So therefore from Laurent series we will get the series function, and it will be f of z is equal to summation n is equal to 0 to infinity n into z minus alpha whole to the power n plus summation over n is equal to 1 to infinity a of minus n into z minus alpha whole to the power minus n. That means compact form of these two series is actually the summation over n is equal to minus infinity. Okay, if we put n is equal to 1 in the second summation, we'll get the first value is minus 1 z minus alpha whole to the power minus n. If we put n is equal to 2, we'll get a of minus 2 z minus alpha whole to the power minus 2. So therefore the compact form of these two summation is equals to summation over n is equal to minus infinity to plus infinity n into z minus alpha whole to the power n. Okay, and where n is equal to 1 by 2 pi I close integration over c1 f of z by z minus alpha whole to the power n plus 1. You know, this is I have already mentioned in the previous slide where n is equal to this. Okay, so the given Laurent series is reduced to summation over n is equal to minus infinity to plus infinity n into z minus alpha whole to the power n. When we put n by minus n in an, and we can write down this equation number 2, and where n is equal to 1 by 2 pi I close integration over c1 f z by z minus alpha whole to the power n plus 1, and where c is the circle of radius say r and with center at the point alpha, and here r is lies within r1 and r2. Okay, now we will move on the next slide. So if the function f of z is analytic within c1, so c1 be any curve, here the curve is a circle and alpha is the point is within the circle c1. Okay, then from Laurent series where n is equal to 1 by 2 pi I close integration over c1 f of z by z minus alpha whole to the power n plus 1 into dz, and if we can apply the Cauchy's integral formula for successive derivatives, we will get f to the power n of alpha by n factorial. N is equal to this. Okay, and from Bn, and you know Bn is equal to 1 by 2 pi I close integration over c1 f of z by z minus alpha whole to the power minus n plus 1 into dz, and it will give 1 by 2 pi I close integration over c1 z minus alpha whole to the power n minus 1 into f of z dz. And now we can apply the Cauchy's theorem. We'll get the value of this integration, or value of the value of Bn. Okay, and it will be 0. Hence in this case the Laurent series 1 reduced to the Taylor series, and in this Taylor series is f of z is equal to summation over n is equal to 0 to infinity and z minus alpha whole to the power n by n factorial into f to the power n of alpha, and this is the mathematical expression of Taylor series, you know. So in this section I have discussed about the how to find the Taylor series from the Laurent series. Okay, and now when we put alpha is equal to 0 in the Laurent series 2, I mean to say this one, okay, this equation, when we put alpha is equal to 0 in this equation, we will get the value of f of z. Okay, that is the series function of f of z, and it will be f of z is equal to summation over n is equal to 0 to infinity n into z to the power n. Okay, but n is equal to 1 by 2 pi I close integration over c f of z by z to the power n plus 1 into dz. So before we start some example on Laurent series, we will discuss some basic concept of Laurent series. The working procedure for finding the Laurent series of a function f of z would be more simpler if f of z can be expanded into an infinite series by using the binomial expansion, subject to the restriction on Z, the obtained infinite series is nothing but the required Laurent series. See the following examples. So here is the example. The first example is expand the function f of z, z square minus 1 by z plus 2 into z plus 3. Okay, that means we want to find the Laurent series when modulus of z is less than 2, and second one is when the modulus of z is lies within 2 and 3, that is 2 less than modulus of z less than 3, and the third problem we'll discuss when the modulus of z is greater than 3. So in this three condition, what will be the Laurent series for the function f of z? You know, in this three part the Laurent series are not same. So there are different Laurent series for different region. Here is the solution. Let f of z is equal to 1 plus. So this is actually the function f of z. So f of z is equal to z square minus 1 by z plus 2 into z plus 3. So can be decomposed into the partial fraction 1 plus a by z plus 2 plus b by z plus 3. So from this we will get the value of a and b. Okay. So now simplifying this equation, we'll get, when we put z is equal to minus 2 and z is equal to minus 3, then from this we'll get a is equal to 3 and b is equal to minus 8. Therefore the given equation or given function is can be written as 1 plus 3 by z plus 2 minus 8 by z plus 3. Now we are going to find the Laurent series expansion when the circle is modulus of z is less than 2, that is in the region modulus of z less than 2. So here f of z is equal to 1 plus 3 by z plus 2 minus 8 by z plus 3. After decomposed we will get this one, okay, for the given function. So from this we will get, when we common or 2 from denominator, we will get 1 plus 3 by 2 into 1 plus z by 2 whole to the power minus 1. Okay, and in the third part or third term, when we take 3 as common, we will get minus 8 by 3 into 1 plus z by 3 whole to the power minus 1. And 1 plus x whole to the power minus 1 is, this is the series function, and it will be 1 plus 1 minus x plus x square minus x cube plus x to the power 4. That is the alternative term are all negative. And similarly the series function for 1 minus x whole to the power minus 1, and it will gives 1 plus x square plus x cube plus x to the power 4, okay, and up to infinity. So these are the series function, and I have already discussed in the previous lecture on Taylor series, and therefore, so this is the series function 1 plus z by 2 whole to the power minus 1, and it will gives 1 minus z by 2 plus z square by 2 square minus z cube by 3 cube 2 to the power 3 plus z to the power 4 by 2 to the power 4 and up to infinity. That is the alternative term of negative. As well as 1 plus z by 3 whole to the power minus 1, and it will gives, if we apply the Taylor series or the binomial expansion it will give 1 minus z by 3 plus z square by 3 square minus z to the power 3 by 3 to the power 3 and up to infinity, which hold for z by 2 is less than 1, okay, as well as z by 3 is less than 1. So from this 2 we will get this function or this series will hold for modulus of z is less than 2. Therefore f of z, this is the composite form. So 1 minus z by 2 plus z square by 2 square can be written as a composite form, or can be written as a summation n is equal to 0 to infinity minus 1 whole to the power n into z by 2 whole to the power n, and similar thing will happen in the second part of the series. So here we can write it summation over n is equal to 0 to infinity minus 1 whole to the power n into z by 3 whole to the power n. This is the Laurent series when modulus of z is less than 2, and it will be f of z is equal to 1 plus 3 by 2 into summation over n is equal to 0 to infinity minus 1 whole to the power n z by 2 whole to the power n minus 8 by 3 summation over n is equal to 1 to infinity minus 1 whole to the power n into z by 3 whole to the power n. Let's move on the next part of this example. So when the function is defined in the region 2 less than modulus of z less than 3, that is the annular region bounded by C1 and C2, where say C1 is equal to the circle whose radius at the radius 2 and the circle whose radius is 3, and these two circles are concentric circles. So that means this region is actually the annular region between the circles C1 and C2. Okay, so therefore from the given equation, and this the given equation is f of z is equal to, okay, this one is actually, so f of z is equal to 1 plus 3 by z plus 2 minus 8 by z plus 3. So okay, in this region, what will be the change of Laurent series? So first of all, from the second term we'll take z as common, and from the second we'll take 3 as common, okay, on denominator. So if we take z as common on the second term, we'll get 1 plus 3 by z into 1 plus 2 by z whole to the power minus 1, and from the third term when we'll get 3 as common, and it will give 1 plus z by 3 whole to the power minus 1. So these two functions are the series function, and now we can apply the binomial expansion of these two functions, and it will give, the first function will give 1 minus 2 by z plus 2 square by z square, then minus 2 to the power 3 by z to the power 3, and up to infinity. And the second function, that means 1 plus z by 3 whole to the power minus 1, after using the binomial expansion, and it will give 1 minus z by 3 plus z square by 3 square minus z to the power 3 by 3 cube, okay, and up to infinity. And the composite form, that is within summation, and this series function will gives 1 plus 3 by 2 and 3 by z into summation over n is equal to 0 to infinity minus 1 whole to the power n into 2 by z whole to the power n. So this series function can be written as a summation within minus 8 by 3 into summation over n is equal to 0 to infinity minus 1 whole to the power n into z by 3 whole to the power n. This is the composite form of the function f of z. This is actually the series function within the summation. So this will happen when modulus of 2 by z is less than 1. If modulus of 2 by z is less than 1, that means modulus of z is greater than 1, then this series function will valid. As well as when modulus of z by 3 is less than 1, that means modulus of z is less than 3, then the second series is valid. That means the second series is valid when modulus of z is less than 3. Okay, and after that we are going to talk about the third portion on example 1, and we are going to find the Laurent series when modulus of z is greater than 3. So in this case the function will be changed, and that means the series will be changed. Okay, so in the first case that means modulus of z is greater than 3, that means when modulus of z is greater than 2 as well as modulus of z is greater than 3, so combining these two will get modulus of z is greater than 3. So first of all, from the given function, this one is actually, this is the given function 1 plus 3 by z plus 2 minus 8 by z plus 3. So from the second term, what will be common from denominator? Second term will get z as common, and then the second term will be reduced 1 plus 3 by z into 1 plus 2 by z whole to the power minus 1, as well as when we take z as common from the third term, and then it will be 3 by z into 1 plus 8 by z into 1 plus 3 by z whole to the power minus 1. Then similarly we can apply the binomial expansion. This is the series function, so 1 plus 3 by z into, and it will write in the summation, within summation, summation over n is equal to 0 to infinity minus 1 whole to the power n into 2 by z whole to the power n, as well 8 by z into summation over n is equal to 0 to infinity minus 1 whole to the power n into 3 by z whole to the power n. Okay, so this series function can be written as a summation, and it will be minus 1 whole to the power n into 3 by z whole to the power n. So the second series, and this it will define when 2 by z is less than 1, that means modulus of z is greater than 2, and the second series function will define when modulus of 3 by z is less than 1, that means modulus of z is greater than 3. These all are the series function and different series function for different region. So first series function, I have got f of z is equal to this. Okay, in the region modulus of z less than 2. In the second portion, where the where mod of z is lies within the circle C1 and C2, where C1 and C2 are the concentric circle, and whose radius are 2 and 3. That means this series will define in the annular region C1 and C2. Okay, and the third portion, where the region is outside the circle, modulus of z is equal to 3. Okay, so that is modulus of z is greater than 3. So in this region we will get the Laurent series, and it will be this. Let us move on the next problem on Laurent series. Here is the example. So expand the function f of z is equal to 1 by z minus 1 into z minus 2 between the annular region modulus of z greater than 1 and modulus of z greater than 2. So here is the solution of the given problem. So let's start. The given function can be written as, after if we apply the partial fraction on this function, and it will give f of z is equal to 1 by z minus 2 minus 1 by z minus 1. So the function we are going to find the series function, or series, that means Laurent series between the annular region modulus of z is equal to 1 and modulus of z is equals to 2. That means 1 less than modulus of z less than 2. So in that region we are going to find the Laurent series. Okay, so that means 1 less than modulus of z less than 2 is actually, there are two circles whose center at the point alpha, say 1 less than modulus of z less than 2. That means there are two circles, and two circles are concentric circle whose center at the point 0, 0, and say C1 is equal to a circle modulus of z is equal to 1, and C2 is the circle where modulus of z cell is less than 2, and first circle is modulus of z is less than 1. So in this section we are going to find the Laurent series in the region 1 less than modulus of z less than 2. That means in the annular region bounded by C1 and C2. Okay, so then the function f of z can be put 1 by z minus 2 minus 1 by z minus 1. After decomposed of the partial fraction, we will get this one. Okay, so f of z is equal to 1 by z minus 2 minus 1 by z minus 1. So the region is actually 1 less than modulus of z less than 2. That means from the first term we will take 2 as common, and from the second term we will take z as common. Okay, so from first term we will take 2 as common, then it will reduce to minus 1 by 2 into 1 minus z by 2 whole to the power minus 1. Okay, if we take 2 as common, then it will gives this, and then it will gives 1 minus z by 2 whole to the power minus 1. As well, when we put z as common from the second equation, and it will give minus 1 by z into 1 minus 1 by z whole to the power minus 1. So now applying the binomial expansion of these two terms, 1 minus z by 2 whole to the power minus 1, as well 1 minus z 1 by z whole to the power minus 1, and it will give the within summation minus 1 by 2. Actually this is the series function. After applying the binomial expansion, it will gives 1 minus 1 by z plus z square by 2 square minus z cube by 3 cube. Okay, and the composite form, that means the summation form, or and composite form, that means the series function can be written as a summation, and it will be minus 1 by 2 into summation over n is equal to 0 to infinity z by 2 whole to the power n, and a similar thing will happen in the second part, and from second part it will gives minus 1 by z into summation over n is equal to 0 to infinity 1 by z whole to the power n. Okay, so these two terms, that is in the first term, and it will holds when z by 2 is less than 1. That is the first series will define when modulus of z by 2 is less than 1, that means modulus of z is less than 2. As well, when modulus of z 1 by z is less than 1, then the second series will define or hold. So in this case 1 by z is less than 1, that means modulus of z greater than 1. So the series function f of z is equal to this, the first and second one. So two functions or two series function, both are holds when modulus of z is lies within 1 and 2, and therefore f of z is equal to this, that is minus 1 by 2 summation over n is equal to 0 to infinity z by 2 whole to the power n minus 1 by z into summation over n is equal to 0 to infinity 1 by z whole to the power n, which is the required Laurent series in the region 1 less than modulus of z less than 2. That means in the annular region bounded by the two concentric circle, and the radius of the circle are 1 and 2. Clear? After that we'll move on the third problem. So here is the third problem. Find the Laurent series of the function f of z is equal to e to the power z by z minus 2 whole to the power 3 about the point z is equal to 2. That means we are going to find the series about the point z is equal to 2. So this is the slightly difference problem. That is, this problem is slightly different from the problem 1 and problem 2. So here is the solution of the given problem. So let first we consider z minus 2 is equal to u. Okay, so from this we will get the value of z. So from this we will get z is equal to u plus 2. So now putting z is equal to u plus 2 on the given function e to the power z into z minus 2 whole to the power 3, and from this we will get e to the power, where z is equal to u plus 2, so e to the power z will be reduced to e to the power u plus 2, and z minus 2 whole to the power 3 is replaced to u to the power 3, and u to the power e to the power u plus 2 can be written as e to the power u into e to the power 2, where e to the power 2 is the constant function by u to the power 3, and e to the power u is a exponential function, and you know the after using the binomial expansion or the Taylor series expansion, we will get the value of e to the power u, or we will get the series of u to the power u. So series of u to the power u is equal to 1 plus u square by 2 factorial, you know, plus u to the power 3 by 3 factorial, and up to infinity. Okay, and now, and from this we'll get e to the power 2 into, now we divided e to the power 3 on this series, and it will reduce to e to the power 2 into 1 by, the first term is 1 by e to the power 3, after divided by u to the power 3, 1 by e to the power 3 plus 1 by e to the power 2 plus 1 by 2 factorial into 1 by u plus 1 by 3 factorial, okay, 1 by 4 factorial into u, after divided by u, will get this series. And now we replace u as z minus 2 from this series. We will get e to the power 2, this is the first term, e to the power 2 by z minus 2 whole to the power 3, where u is equal to z minus 2, as well as the second term, it will be e to the power 2 by z minus 2 whole square. Third term is 1 by 2 factorial into e to the power 2, okay, by z minus 2, and up to infinity. So this is the series function. This is the series about the point z is equal to 2, and this series is called a Laurent series. And this series will we have obtained. And now we are going to the last problem of today's lecture. Expand the function f of z is equal to z by z square minus 3z plus 2 when modulus of z is less than 1. Number 2, when 1 less than modulus of z less than 2. And number 3, when modulus of z is greater than 1. So there are three regions. The first region is modulus of z less than 1, that is in the circle whose center at the point 1. In the second case, in the second problem, where the center at the point 0 and the radius are r1 and r2. So these two circles are concentric circle, and we are going to find the Taylor series in the region, that means the annular region bounded by C1 and C2. And in the second case, and in the third case, where the function, that is we are going to find the Laurent series in the region, that is the region outside the circle, modulus of z is equal to 2. Okay, let us consider the function f of z is equal to z by z square minus 3z plus 2, and this function can be written as fz is equal to z by z minus 1 into z minus 2. So after using the middle term method, we will get z by z minus 1 into z minus 2. Okay, from the theory of partial fraction, you know, there are two constant a and b. Okay, so these two constants are arbitrary constant. So therefore any function z by z minus 1, here is the function z by z minus 1 into z by z minus 2, can be decomposed into two partial fractions. Okay, so the first fraction is a by z minus 1, and the second fraction is b by z minus 2. So where a and b are the arbitrary values. So after decomposed, we will get a into z minus 2 plus b into z minus 1 by z minus 1 into z minus 2. Okay, now letting z is equal to 1 in this section, we'll get the value of a, and it will be minus 1, a is equal to minus 1. And when we letting z is equal to 2, and we see b is equal to 2, value of b is equal to 2. Hence the given function f of z is equal to z by z minus 1 into z minus 2 can be written as 2 by z minus 2 minus 1 by z minus 1. So now let D1 is the region. So that means D1 is the circle, and all the points within C such that modulus of Z less than 1, and D2 is the circle where the points lies within the annular region bounded by the circle whose radius is 1 and the circle whose radius is 2, as well as D3 is the circle, that is all the points whose lies outside the circle modulus of Z is equal to 2. So the circle whose center at the point 0 and radius is 2. Okay, so there are three circles, D1, D2 and D3. The first circle where the points are lies within the circle modulus of Z less than 1, that is in the region modulus of Z less than 1. D2 is the region where this is the annular region between C1 and C2. Say C1 is the circle whose radius is 1 and C2 is the circle whose radius is 2, and D3 is the region is outside the circle modulus of Z is equal to 2. So we'll move on the next slide. So this is the points Z. Okay, for Z belongs to D1. So for all Z belongs to D1, so the points lies within the circle D1. That means modulus of Z less than 1. So we find the Maclaurin series around the circle D1. Okay, so you know f of Z is equal to 2 by Z minus 2 minus 1 by Z minus 1. So from this we'll get 1 by 1 minus Z minus, and from the first term we'll take 2 as common, and from this we'll get 1 by 1 minus Z by 2. Okay, so therefore from the first term, if we can apply the binomial expansion, we'll get summation over n is equal to 0 to infinity Z to the power n. This is the series function, 1 minus Z whole to the power minus 1, and it will be 1, the first term will be 1, second term Z plus Z, third term Z square, after that the fourth term will be Z cube, okay, and up to infinity. So in summation it will be summation n is equal to 0 to infinity Z to the power n. As well as in the second term we'll get the series function as well, and it will be summation over n is equal to 0 to infinity Z to the power n by 2 to the power n. Okay, so therefore this expression, this is actually the required Laurent series, or this expression are valid when modulus of Z is less than 1 and modulus of Z by 2 is less than 1. So that means modulus of Z is less than 1 as well as modulus of Z is less than 2, and from both it holds modulus of Z is less than 1. Okay, let us move on the second part of this problem. This is the second part. When Z belongs to D2, we find the Laurent series of the function f of Z. Okay, that means in that case where this is the annular region bounded by the two concentric circle C1 and C2, say, where C1 is the circle whose radius 1 and C2 is the circle whose radius is 2. So in this case we are going to find the Laurent series when 1 by Z, modulus of 1 by Z is less than 1, as well as modulus of 2 by Z is less than 1. So from this we'll get modulus of Z is greater than 1 as well as modulus of Z is less than 1. Okay, so therefore from the first term of the given function we'll take Z as common. Okay, and from the second function we'll get 2 as common. So therefore from first function after we get Z as common, and it will be minus 1 by Z into 1 by 1 minus 1 by Z, and in the second problem it will gives 1 by 1 minus Z by 2. So 2 as common from denominator and numerator, 2 is cancelled. Okay, so it will gives this 1 by Z 1 minus Z by 2. So this is the series function, 1 by 1 minus z whole to the power minus 1, and it will give summation over n is equal to 0 to infinity 1 by z to the power n as well in the second case. And this is also the series function, 1 minus 1 by z by 2 whole to the power minus 1. We will find the series function, and it will be summation over n is equal to 0 to infinity z to the power n by 2 to the power n. Therefore, this equation, this expression gives summation over n is equal to 0 to infinity 1 by z to the power n plus 1 minus summation over n is equal to 0 to infinity z to the power n by 2 to the power n. And after that we'll take, now if minus 1 as common, then from this this expression will be minus of summation n is equal to 0 to infinity, this is the second term, in z to the power n by n factorial, plus summation over n is equal to, okay, when we start this summation from n is equal to 1, then it will be changed and it will be 1 by z to the power n. So this is the required series, Laurent series for the given function, and this expression or this series function will be valid when modulus of 1 by z is less than 1, that is modulus of z is greater than 1, and z by 2 is less than 1, that is modulus of z is greater than 2. Okay, that is, therefore this is the required Laurent series expansion in the region 1 less than modulus of z less than 2. And this is the last part of today's lecture. When z is lies within the circle C2, then find the Laurent series expansion of f of z. So in this case, when modulus of, so in this case we are going to find the Laurent series expansion when modulus of 1 by z is less than 1 as well as modulus of 2 by z is less than 1. That means modulus of z is greater than 1 as well as modulus of z is greater than 2. From the given function, we will take z as common from the first term and z as common from the second term. We will get this expression, that is minus 1 by z into 1 by 1 minus z, 1 minus 1 by z. In the second case, we will get plus 2 by z into 1 minus 2 by z. Okay, and this is the, this is the series function I have already mentioned in the previous example, or in this example on first part as well as in second part. And this one will give summation n is equal to 0 to infinity 1 by z to the power n, as well as in the second part it will give 2 by z into summation n is equal to 0 to infinity 2 to the power n by z to the power n. Okay, so and after that this expression will reduce to minus summation over n is equal to 0 to infinity 1 by z to the power n plus 1 plus summation over n is equal to 0 to infinity 2 to the power n plus 1 by z to the power n plus 1. And from this expression, it will give summation n is equal to 0 to infinity 2 to the power n plus 1 minus 1 by z to the power n plus 1. That is summation over n is equal to infinity 1 to infinity. When we start with n is equal to 1, then this expression will be changed and it will be 2 to the power n plus 1 by z to the power n. And this is the required Laurent series expansion. This expansion will valid when modulus of 1 by z is less than 1 as well as modulus of 2 by z is less than 2. So from this, from both, we will get modulus of z is greater than 2. Okay, we will stop here. Thank you.